Hello everyone. In this video, we'll be talking about using linear programming to solve transportation and transshipment models. So I have a separate set of slides for this, and we'll be using those slides instead of the ones from the textbook, right? So the transportation and transshipment models are part of something called basic network models. So a network model is one where you can use a network to represent the way the system works. So by network, you mean you have nodes that represent locations. Nodes are usually represented as circles or ovals, and then arcs or arrows, which represent possible routes that you can take. There are two basic network problems that form the foundation of supply chain design, and those are the transportation problem and the transshipment problem. And we'll go over both of them in this video. Just to be clear, the transshipment model is not in the textbook, but the everything that you need for that will be right here. Okay, so let's get the transportation model. So the transportation model is used in a scenario where you have supply locations with known capacities, and these goods have goods available, and these goods have to be transported to demand locations where you know the demand at each of these locations. So if supply locations with known supplies, demand locations with known demands, and the objective is to find which supply location serves which demand location, and you want to do all of this at a minimum transportation cost, right? Now there are no intermediate locations. Goods flow directly from the supply location to demand locations, right? And we will assume that each of the supply locations has a supply of S sub I, and each of the demand locations J has a demand of D sub J. So S sub I for supply and D sub J for demand, and the cost of shipping from location I, from supply location I to demand location J will be represented as Cij, right? So what does all of this mean? So here is this representation of a simple transportation model. You have two supply locations, S1 and S2. So when you say S sub I, you're talking about 1 and 2, with supplies S1 and supply S2 here. So this supply could be 100 and this supply could be 100. Then you have different demand values. So you have three demand locations, 1, 2, and 3, and the demand at each of these locations is D1, D2, and D3. And the cost of transporting anything from, oops, I think this is messed up right there. Should be 1. Sorry about that. There you go. Right. So cost of transporting from supply location 1 to demand location 1 is C11. From supply location 1 to demand location 2 is C1 to 2, 1 to 3, right? Then 2 to 1, 2 to 2, and 2 to 3. So those are the different cost values. So the idea is figuring out how these supply values get allocated to these demand locations at minimum transportation cost, right? So simple enough problem, nothing too complicated. We will use a linear programming, a linear optimization model to do it. Now, you might have seen linear programming before, you might not have. In either case, I will go over all the major parts of it right here. There are three big things to major parts to a linear programming problem or linear optimization problem. You need to figure out what your decision variables are, then you need to figure out what your objective function is and constraints. So think of any decision that you make. So if you're either making a single decision, you're making a group of related decisions. And the way linear optimization problems work is for all the decisions that you make, you assign variables, either one or multiple variables to each of the decisions that you make. Then using that, you create a mathematical function that represents your objective. And in most business scenarios, objective will either be to maximize profit, minimize cost, maximize sales or revenue, minimize time. So these are the big sorts of objectives that you end up seeing. Now, finally, and most crucially, you will also have to represent constraints. So constraints are you will have limited manpower or limited material or something limiting you. In this case, you have limited supply at supply locations, and you have a certain demand at demand location. So either all demand has to be satisfied, or you cannot supply more than a certain amount of supply from a supply location. So all of these form constraints. And the way you represent constraints mathematically is either using equations or inequalities, right? And that's something to keep in mind. Now, we'll begin with decision variables. So in this problem, we will represent the number of decision variables will be equal to the number of arrows or lines that you see here. Each line will be a decision variable representing the number of units that get transported from, say, this location to this location. So if you have a decision variable xij, that is the number of units shipped from origin I to destination j, or supply location I to demand location j. So x11 in this case will be the number of units that get shipped from supply location 1 to demand location 1. Similarly, you'll have x12, like you have c12. C12 is the cost of shipping one unit. X12 will be the number of units that you ship. C13 is the cost of shipping one unit from 1 to 3, and X13 will represent the number of units that you ship from 1 to 3. So with that in mind, what you can do is you can write the objective function. So the objective function is to minimize the total transportation cost, which is you multiply the cost with the number of units that you're shipping and you add all of them up. So all the supply location, all the demand locations, you look at all possible combinations, you add up all the cost values, and that is the objective function. All right. Now, the constraints. So in these transportation problems, the number of constraints are usually equal to the number of nodes that you have, which tell you that you're constrained on the supply. You have a certain amount of supply available and you cannot supply more than that. And then you have demand. So you have to, in most cases, you have to supply all the demand in the demand location, right? Now, when you have a network like this with supply locations and demand locations, there are three possibilities. One possibility is that total supply is more than total demand, in which case you have too much supply and you will not be using up all the supply that's available at the supply location, but you will be able to satisfy all demand that you have at demand location. So that's the first scenario where total supply is more than total demand. Second scenario is where total supply is exactly equal to total demand, in which case you're using up all the supply and you're able to satisfy all demand, right? So all supply gets used up, all demand gets satisfied. That's the second scenario. The third scenario is where demand is more than supply, in which case you will use up all your supply, but all demand will not be satisfied. And it is important to know which of these three scenarios you are in. Are you in too much supply scenario? Are you in too much demand scenario? Or are you in a balanced scenario? Now, why is it important? Well, when you write your constraints depend upon the type of constraints that you write will depend upon which way the balance is shifting. So let's first look at the most common scenario where total supply is more than total demand. So you're saying that if you add up all the supply values, it is more than if you add up all the demand values. So if supply is more than demand, then when you write the supply constraints, you're saying that all the way the supply constraints work out is you're saying all the supply going out of this location 1 has to be less than or equal to the supply that is available. So let's look at this constraint again. So all the supply going out of all supply locations I, from supply location I to all demand locations j, has to be less than the supply that's available. So two things here. First, you're adding up all the x's. So you'll say x11, x12, x13. So the supply location will be fixed, but you're looking at all three demand locations. So everything that gets transported from this particular supply location to all the demand locations. So you're adding up all the x's. That has to be less than or equal to the supply. Why less than or equal to the supply? Because we are assuming the total supply is more than total demand, which means that not all the supply gets used up. So let's say that the supply here is 100, supply here is 100, but demand is 50, 50, 50, in which case 50 units of supply doesn't get used up. So you're saying that the total supply coming out of each of these locations shouldn't be more than 100, which is the supply that is available at each of these locations. So you might just use up 90, or you might use up 80 or 50 or 60 or some other number, but it will not be more than 100, right? So that's the first thing. So that's why we write less than or equal to. And then finally, when you write demand, now in this case, we wrote demand is equal to, again, it is very important to understand. This is the scenario where total supply is more than total demand. So that is why you're saying that all demand gets satisfied. So because all demand gets satisfied, demand constraint is an equal to constraint, right? Right. So you're saying that all the supply coming into this demand location has to be equal to the demand at this location. So it'll be x11 plus x21 is equal to the demand here. Similarly here, x12 plus x22 will be the demand here, and x13 plus x23 will be the demand here, right? And it's equal to because we are assuming supply is more than demand. Now, whichever is more, if total demand were more than total supply, right? So if total demand were more than total supply, then demand constraints will be less than or equal to, and supply constraints will be equal to, right? So which side you put the equal to depends upon which side is more. If demand is more, if supply is more, all supply constraints are less than or equal to, all demand constraints are equal to. If demand is more, then all demand is less than or equal to, and supply is equal to. But if both supply and demand are exactly equal to each other, so you have a balanced system, then you can write all your constraints as equal to constraints, right? All of them have to be equal to constraints. So that's something to keep in mind. Okay, let's look at an example here. So Bennett and Daughters have orders. Daughter is a company that has orders for 80,000 widgets from at three different client locations. So three different client locations are Longbourn, Eastbourne, and Bath. And there are two plants that Bennett and Daughter own, and each of these plants can make 50,000 widgets each. Now the demand at Longbourn is 20,000, demand at Bath is 10,000, and demand at Eastbourne is 60,000, right? So that's the data that we have. So the question is, how do you allocate these orders? So what we'll do is we will set it up as, so these equations that we have. So we'll set up these equations, but we'll do the setting up in Excel directly. We don't have to write the equations down. It's much easier to set this up in Excel, and that's exactly what I am going to do. Yeah, this data I can just copy. What the hell? Sorry. Right. Okay. All right. Okay. Okay, we have Longbourn, Eastbourne, and Bath. So these are the cost values. So the way you set it up is you first always start with the cost values. Don't want them to have text values. Right. Okay, let me make this bigger. Okay, now the first things first. So let's we have the capacity for each of these plants. So each plant has a capacity of 50,000, and then we have demand for each of these locations. So demand for Longbourn, let's quickly look this up. So demand is 20, 60, and 10. Right? So let me, I don't know why I like doing that, but I do. Right. So with this, all of these are dollar values. We can do that later. So the next thing that we do is I'm going to copy this portion here. So these values here, I'm going to color them. And the reason why I'm coloring them is because these are your decision variables. So this is where the final answer is going to show up. So this cell is X11, which represents the number of units that you transport from plant 1 to Longbourn. Plant 1 to Eastbourne is going to be here. Plant 1 to Bath will be here. Then plant 2 to Longbourn, plant 2 to Eastbourne, plant 2 to Bath. So these are the decision variables that you have. So the X11, X12, X13, X21, X22, X23. So those are going to be your decision variables. These are the variable cost values. There are no fixed costs here. So that's something to keep in mind. So let's begin with the first thing, which is the objective. The objective is multiply. So it's 24 times X11. So 24 times the number of units that you transport from plant 1 to Longbourn. Remember, since 24 here is the cost of transporting one widget from plant 1 to Longbourn. So if you transport 10 widgets, it's going to be $240. If you transport 100 widgets, it's going to be $2,400 and so on, right? So these are all variable cost values. So when I write the objective, I have to say, okay, so 24 times the number of units that are transported from plant 1 to Longbourn plus 30 times number of units transported from plant 1 to Eastbourne, number of units so cost times the number of units transported from plant 1 to Bath, and so on. So I have to multiply each of these corresponding numbers together, and I have to add them up. So I can either write the formula individually this way, which is going to take some time, or I can use the function in Excel called sum product. So I can use sum product where I choose the variable cost values, then put a comma. Do not forget the comma. Comma is crucial. And then choose the decision variable. So the variable cost values and decision variable. So this, what it will do is it's going to multiply the corresponding numbers together, sum of products, right? So product is multiplication. So you multiply the corresponding numbers together and you add them all up. So this is where the objective function is going to be, right? Now the constraints. So you have two supply constraints. So let's say supply constraints. Spell it correctly. So supply constraints, so we have amount that is supplied and then supply available. So you have two plants that can supply for you. So what is the amount supplied from each of these plants? Actually, let me. All right, so these are my supply constraints. So for plant 1, I'm going to say, what is the total amount supplied out of plant 1? It has to be less than or equal to the supply available, which is its capacity, right? So supply available is just equal to its capacity. So what is the total amount supplied out of plant 1? So total amount supplied out of plant 1 is the amount that is supplied from plant 1 to Longbourn, Eastbourne, and Bath. So you add up all the values that are transported from plant 1 to the 3 locations, and that will be the total amount supplied, and that has to be less than or equal to the supply that's available. Just copy these formulas down and that should work. So this is all the supply that's available, that's shipped out of plant 2, and that has to be less than or equal to the supply that's available at that location, right? So 50,000 units are available. These 50,000 units will be somehow distributed to the 3 locations. So these numbers here by the end of the day. So this is where your final solution is going to show up. This will tell you, say, 5,000, saying that from plant 1, you will send 5,000 units to Longbourn. Say 2,000, plant 1 to Eastbourne, and 5,000 from plant 1 to Bath. So whatever numbers come out, they will come out. But you don't have to worry about what the numbers are going to be. The solution is going to come from Excel. So we'll use, Excel has this tool called Solver. We will use the Solver tool to do this solution. Again, if you've done this before, great. If not, I hope you're following me. Okay, now let's do the demand constraints. So supply constraints, I did them as rows. I'm going to do demand constraints as columns. This is the amount supplied and the demand. Right? So the demand at Longbourn is 20,000, demand at Eastbourne is 60,000, and demand at Bath is 10,000. So we know those values, right? Oh, one thing we didn't check. So if you look at this, total supply is 10,000 units, and total supply is 100,000 units. Total demand is 90,000 units, which means that total supply is more than total demand. So when we write our constraints, the supply constraints will be less than or equal to, and demand constraints will be equal to constraints, because supply is more than demand. Total supply is 100,000, total demand is 90,000, right? So amount supplied to Longbourn is the sum of everything that comes from plant 1 and plant 2 into Longbourn. So just add up everything in this column, right? So that's why I wrote this as columns, so I can just copy this formula out like that. This is everything supplied to Bath from both locations, and this is everything supplied to Eastbourne from both of the plant locations. That's it. So we have set everything up. What we'll do is we'll put this into something called the solver. Now, bringing up, so solver is not automatically, so it's already there in all on all Excel sheets, but you might not be able to see it. So if you go to data, you should be able to see solver here. It's similar in both Windows and Mac. If you don't see solver here, the way you bring it up in Windows and the way you bring it up in Mac is very different. In a Mac, it's easier. So what you have to do is you have to go to tools, and you will notice something called Excel add-ins. Then you go and make sure that you check the box next to the solver add-in and you click OK. Now, if you're on a Windows computer, because I don't have one, I can't show you here. What you can do is you can you can go to YouTube and say, how do I bring up the solver? And it's a very, very simple process. You just have to make like 3 or 4 clicks. You have to go to add-ins and make sure that you check the box next to Excel to the solver add-in, and you're okay, right? So I'll assume that you did that. So once you do that, the solver tool comes up here. So click on solver, you'll notice that it looks like this. So we have the objective function here, we have the decision variables here, and we have the constraints here. Now, few things. Make sure that this box is always checked, because all our variables are positive. And then this is, you have to say LP for linear. We don't want non-linear, we want linear, right? Okay, so first, this is a cost minimization problem. So I'm going to choose minimize. And the objective for me is in this cell right here. That's where I wrote the formula for the objective. And that's my objective. So A12, that's where I wrote it. So it'll be A12. Now the variables. So these are all the variables that I have. And that's why I like coloring them, so I know exactly where they are. So these are all my decision variables, right? And then my constraints. So first I'll write the supply constraints, then I'll write demand constraints. So you can write the constraints one by one, or you can group them together. So I'll group them together. So if I click on add, I'll say that the total amount supplied to both of these plants 1 and 2, have to be less than or equal to the supply that's available at both the plants. So by choosing both of these on the left hand side and the right hand side of the constraint, I can write them both at once rather than doing them one at a time, right? So it will show up as B16 to B17 is less than C16 to C17. So B16 will be less than C16 and B17 will be less than C17, right? That's my supply constraint. Now for demand constraint, so all the amounts that are supplied to the three different locations have to be equal to the demand at these locations, right? It's an equal to constraint, so I'm going to choose equal to in the middle. And there you go. So once you've written your supply constraints, your demand constraints, put in your variables, done your objective and all of that, the only thing left to do is to click on solve. Click on solve and the solution will show up. We don't have to do anything about it, and it's usually instantaneous. These are pretty simple, straightforward problems, right? So what this is saying is that from plant one, all the materials from all the widgets that you make in plant one go to Eastbourne. Nothing goes to Longbourn, nothing goes to Bath. But from plant two, you are supplying some to Longbourn, some to Eastbourne, and some to Bath. And these are the number of units that you supply to. And this is the objective, so this is the cost, right? So I'll make this a dollar value with 901 decimal places. So $2.92 million, and this is the minimum. So remember, we wrote this as a minimum cost. So you cannot do this given these dollar values. You cannot do this for less than 2.92 million. That's the cheapest that you can do. Any other option that you pick will be more expensive than 2.92. So this is an optimization problem, which means that this gives you the best possibility, right? So this is the transportation model. I will do the transshipment model in a different video. I'll see you all there, right? Take care.